Good morning. So tomorrow is a special day for our engineers.
Sir.
You know that Engineers Day,
Don't
15th
know, sir.
September.
We don't know.
It is Engineers Day on 15th September. Okay. So actually, you have to enjoy tomorrow.
Okay, sir.
We'll have some program in our. You can join. Maybe links maybe sent. I don't know what they are doing, but something is going like that. Okay. In continuation to the last lecture, some part were left behind. So this is the two definition. This is very important. There are some more things actually. Like here I have written resilience and toughness. Hardness, what is hardness? What is brittleness? So those kind of definitions are also very important. Okay, you can write it down and tell me once you have completed. Is it visible? Oh, is it visible?
Hello, sir.
Yes,
Hello.
I can hear you. I can hear you. Hey,
Hello. I think
write in the chat box.
last time we reached at what formula, sir?
Pardon?
Last time we have we have not completed that formula, right?
We have completed, I think.
Last time we reached to that
Where?
completed, sir. Okay.
I think last time it was completed. Anyways, if it is not completed, I will complete it. You show me the last line of your recording last class.
We have written U is equal to integration to volume sigma x
Uh,
square by 2e dv.
Someone please help him now. His network is not working. I cannot understand. Someone please pass the what you want to say. Ilyas, Bhagirath, you can do it list. That fellow is trying to do something, say something. No, you have, his voice is breaking. So still he is trying. He's a nice fellow. So you should also be conscious about the things, whatever you have not got. Every time he is telling about these things. So Ilyas, what he is saying actually? Do you understand? Yesterday, did I complete that everything?
Yes, sir.
Or it
Yes,
was
sir.
suddenly cancelled due to the time limitation. You at least give me the last line of your notes on that yesterday class. Okay, so that I can understand up to where you can try. So this is the thing I think he is telling, but because of his network issue, his voices are breaking. So please help him actually. He is trying to do something. You are not backing him up. You people at least backing him up, no? So do it. Or is it complete or not? This screen?
Completed, sir.
Okay. So you have to help your friend. Somebody if want to say something but he is not able to express, you have to help him. Okay, now you have to draw one diagram. So that diagram is very informative actually. See how. I'll show you. This is strain, this is stress. Then drop a perpendicular line from here to here. Okay, put some dash line. Then draw another curve. Draw a line, perpendicular line. Okay, so this is actually perpendicular line. So take a point here and drop a perpendicular line. This is also perpendicular. So mark this with another shadow. Okay. Then from here you draw line like this. I am showing the various region under the stress strain curve. So mark this point as F. Suppose this region is D. This region I am putting like this. So let me do one thing.
তার করে কি? হ্যাঁ।
Yes,
করো। তাই কর।
yes. Any problem? So take this region. This point is your F. Okay. So what is this curve? This curve is for tougher material because tough material is that which is having more surface area under the stress strain curve. So this area under this curve, okay, so area under this curve if you look at is more than this curve. Okay, so this is a tough material. And what about this? This is a strong material. Why strong? Strong material. Why strong? You know? See, its sigma value is high, ultimate, that is UTS, sigma UTS. And here you see sigma UTS is below. This is sigma UTS for the other material. So it is below. So it is a strong material, it is a tough material. Okay. Then this portion, let me select another color. So this portion is your elastic resilience. Since it is under the elastic region, so it is your elastic resilience. So what is resilience? Resilience is the ability of a material to absorb energy. Okay. So as a human being, if I want to say, do you want to strong man or do you want to tough man? What would you like to have? Which quality? Can you hear me?
Sir.
Can you hear me?
Yes, sir. We can hear you, sir.
Which quality do you want to have in you? Tough or strong? You want to be tough or you want to be strong? See, let me clarify this point very in a normal way. Strong material is that it can hit anyone, but sometimes if some more strong material hit it, it will get broken. Okay, so it may get break. But the tough material is that though it is not having such a huge strength, but still it can absorb whatever people says. Like if it is a tough man, that means he can absorb all the negativity, because we people are surrounded by negativity. That's true. Everybody is disappointed with their job, everybody is disappointed with their families, with their societies, everything. Okay, now the pandemic. So the people who can stand with this kind of situation, he is a tough man because he can stand against all this negativity. So tough material is that which can absorb all the energy. If you put a hammer on it, if you throw it inside a machine or anything, it can handle or it can absorb the negativity, or rather we can say it can absorb the energy. But strong material, it can break something, but something which is more stronger than it, if it comes in front of it, then it will definitely break. So that is strong material, and that is the difference between strong material and tough material. So as a people, okay, we want to be tough actually. So there was a jeans earlier, probably you are not knowing about that. In our childhood there was a jeans, an ad came given by Akshay Kumar, that was rough and tough. There was jeans called rough and tough. Did you hear about it? Rough and tough jeans, do you know? Are speak at least, this is not academic. No response.
No, sir. Nazar, sir.
So rough and tough jeans was there. So rough and tough, so that is toughness. So he was telling that yesterday I gave up to equation number 4. Let me check. Equation number 4. Wait, huh? I'll just check. If it is not completed, it's not done, I will actually give you tomorrow today. I think it was done. Wait a minute, huh? Up to equation number 4 only I gave. After that, this part was left out. Today I have given. Guru, that day we have completed. Guru, can you hear me?
Okay, sir. Then
Yeah,
It is,
after equation
it
for
is the
that,
final
no?
equation, sir.
So u equal to,
That one is the final equation.
let me read out. U is equal to
Yeah.
integration sigma x square by 2e dv. Equation number 4. And one who has sent me the photo of that is also the same. Ilyas, you have sent, I think. Is it Ilyas? No? No, others Gurung. Okay. That is okay, Gurung. It was over that day. So now you have to draw this diagram to understand the resilience, the strong material, the tough material. Okay?
Okay, sir.
Yeah. So let's move on. Let's
Yes,
move
sir.
on. Yeah. Now one simple question we have to answer. Exercise type. Suppose two elastic bars whose propositions are as shown in figure. I'll draw this figure as shown in R figure R to absorb the figure R to absorb the same amount of energy. Same amount of energy delivered by axial forces at the free end. At the free end. Neglecting stress concentration so you know what is stress concentration? Compare the stresses in the two bodies. Compare the stresses in the two bodies in the two bars. The cross-sectional area area of the left bar is A and that of the right bar is A and 2A. Right. Comment. Comment means comment on your findings. Whatever result you got, you have to comment. Because as an engineer, your duty is not to just solve the problem. You have to explain. You should know the physics of the problem, why it has happened. Okay? So that is very important from an engineering point of view. Explanation. Now let me draw that figure. So area of these two are A, and area of this E of this bigger one is 2A. The length is L, okay, and here it is also L but divided. How? This is your 3 by 4L and this is your 1 by 4L. So ultimately L. So both bars are of same length. Okay. So solution. The bars shown in the figure, is of uniform cross section area. That means these are linearly elastic materials. Means its all properties are same in all directions. Okay. Throughout the normal stress, therefore the normal stress sigma 1 is constant throughout. Is constant throughout. Using the equation. So yesterday you have encountered with an equation. I'm going to write now using equation. So you have got equation like U sigma square by 2E dV. E, why it is happen always? E dV. So this equation you have got. Okay. So this is actually volume integral. Now the thing is that it is a general equation. Now here there are three parts. Okay. So now you have to put one subscript 1 here, so that we are working actually for the first bar, left one. Okay. So this will be sigma 1. This will be sigma 1. Okay. Using this equation and integrating over the volume V of bar, the total energy for the bar is written as so. So for the first bar, for the first not car bar, for the first bar, U1 is equal to your formula volume integral or V, directly you can write sigma 1 square by 2E into dV is equal to sigma by 2 sigma 2 square by 2E integration dV. I'm in a class. I'm in a class. Ah. Tell me, what is it? dV. So ultimately we can write, what we can write? Sigma 1 square by 2e. So area into area into length. Okay. So for the second case or second bar, if it is a bar of variable, see for the second case you see there are two areas, no? One is A, another one is 2A. It is a bar of variable cross sectional area. Would you able to follow me? Area,
Yes, sir.
hence if the stress sigma 2 acts in the lower part of the bar, the stress in the upper part the stress in the upper part is sigma by 2. Okay, because area is double, no? So stress will be half. Area is inversely proportional to your stress. So ultimately U2 sigma square by 2e. This is the basic formula. And why it is happened? This is the basic formula. So here we have to write. So sigma will be divided in two parts. One will be your sigma 2. This is for the lower part, and for the upper part it will be sigma 2 by 2 as we have written by 2e, which will be under whole square dv. If you don't understand, see, ask me some part if you don't understand and why this always happens. Only this is E, right? So finally you will get sigma 2 square by 2e al by 4 plus sigma 2 by 2 whole square 2e 2e, so 2a 3l by 4 is equal to sigma 2 square by 2e by 2e into 5 by 8 al. If both the bars are to absorb same amount of energy, which is given in the question, if the bars Right? Huh? If the bars have to absorb the same amount of energy, that means what? U1 should be equal to U2, or what do we get?
Yes, sir.
U1? Yes? You want to say something?
No, sir.
Okay. So AL is equal to U2 is your sigma 2 square by 2E into 5 by 8 AL. So this AL gone. Okay. This 2E gone. So only what we are living with, we are left with, or sigma 1 square is equal to 5 by 8 sigma 2 square, or we can write sigma 2 is equal to root over 8 by 5 into sigma 1. That means, which gives sigma 2 is equal to, if you take the square root, 1.265 sigma 1. So this is our. Now since you have another adjoint, that is your comment part, so you have to write the what comment, hence only comment, don't like and share, okay? Hence for the same energy load, the stress in the one term I'm going to use, that is reinforced. So reinforced is actually something is uh, what to say, something is enhanced with strength by applying some external agent. Okay, like your RCC, reinforced concrete, cement. So reinforced is some additives you have to add. So the second part we can say the reinforced, because there are two areas. Reinforced bar is 26.5%. 26.5. See, sigma 1 is lesser than sigma 2. So stress in the second part will be higher. Okay, so that is a reinforced part higher than in the plain bar. So stress is much higher than the plain bar. The enlargement of the, somebody please take the snapshot of the attendance and of the enlargement of the cross section. Bhagirath,
Yes, sir.
you are the
Yes, sir.
you are the CR no, of your class.
Yes, sir.
You take the photo. The enlargement of the cross-sectional area, the enlargement of the cross-sectional area over a part of the bar is actually detrimental. This situation is not this situation is not found in design of members for static loads. For dynamic load, it may be different issue, but for static loads, you should not use this type of reinforcement or varying cross-sectional area. Okay, so this is over. So probably for the next topic, we will not have sufficient time. It will take longer time. So better it's not to start today. But I want to say something about the stress concentration. So this is over, no? This is over?
Yes, sir.
Okay. So let me introduce one term. Probably you are encountered with earlier semester. So stress concentration, any idea? What is stress concentration? Any idea? So you know what is stress, that you know, sigma, that is load per area, that you know. But what is concentration? So concentration also you know, from chemistry you know, concentration, molarity, right? So in our material science or in our fluid mechanics, how molarity can come? So actually what is stress concentration? Suppose you have a very pointed tip, okay, and in this point, suppose this point is your A, you put a load over here. Suppose you gave some P load. Let me call this point as B because I am going to introduce A for area. Suppose this is point B. In point B, you have put a load of value P. So here definitely cross-sectional area is very less. So it is almost negligible. That means here stress will be high. Stress will be high. But now if you do it like this, and now take the point B, put the weight P. Now see, your area is not that small. It is significantly high because this area, here the area was very less. So here sigma will be less than this. Okay. So stress concentration is the thing or is the term which is used for this type of pointed tips. So if you have some mechanical uh, arrangement where you have to encounter with this type of thing, then you should make it a blunt type thing. Instead of, you should avoid point type thing, you should apply this blunt type thing. So in many applications you will see that the tip is blunt. For example, if you remember this thing, do you remember what is it? What is it? It is broken Titanic. After accident, this is the Titanic or something else. What is this? Huh? What is this? This is the half part of a Titanic or something else?
Yes, sir.
Titanic. This is not Titanic. This is single point cutting tool. In your workshop theory, lathe machine. Can you remember? So if you take a single point cutting tool, you will see this tip is not pointed. It is little bit rounded. So there is a term called nose radius. So nose radius, there is a term. Probably in your fiber, I think I took it. I also asked about nose radius, this particular nose radius. Okay, so things are little bit blunt or little bit curved. It's not like pointed, so it may get break here. Okay, so that is the stress concentration. If your area of cross section is very less, too less, then the load will be very high at that point. That is called actually your stress concentration. And as an engineer, you should avoid stress concentration while you are designing some mechanical parts. Okay, fine. Okay, then have you taken the attendance? Bhagirath, have you taken